Hey everyone, and welcome. If you're a grade 8 student looking to level up your geometry game, you are in exactly the right place. Today, we're diving into this explainer to unlock some truly fascinating geometric secrets hidden inside a shape you literally see every single day. Yep, we're talking about the circle. Get ready because this is going to be fun. Okay, let's dive into this. Here's a super quick roadmap of what we're covering today. 1. Meet the circle's lines. 2. Radius and tangent right angle. 3. Pause check on tangents. 4. Inscribed angles and arcs. 5. Pause check on inscribed angles. And finally, 6. Recap and transfer question. All right, let's get started. Section 1, Meet the circle's lines. So we've got 3 main players to distinguish here. First up is the chord, which is a line segment entirely inside the circle that connects 2 points. Next is the secant line. Now this one boldly cuts right through 2 points of the circle and just keeps on going. And finally, we have the tangent line, which is a special line that perfectly touches exactly one single point on the very outside of the circle. Let's zoom in on that chord for just a second. By definition, a chord is a line segment where both endpoints lie right on the circle itself. It is contained entirely within the boundary of the circle. And this is actually incredibly important, because chords act as the foundational building blocks for creating other shapes, like triangles, right inside the circle. Now, what's really interesting is how the tangent line behaves. It touches the outside of the circle at exactly one single point. It literally just grazes the edge without ever crossing into the interior. Understanding this unique little grazing point is going to set us up perfectly for our very first big theorem. Which brings us to section 2, radius and tangent right angle. All right, picture this. Step 1. Imagine drawing a radius straight from the center of the circle out to a point on the edge. Step 2, draw a tangent line touching that exact same point on the outside. Step 3, look really closely at where they intersect. Layering these 2 specific lines in this exact way always creates a perpendicular intersection. They form a perfectly square 90-degree angle every single time. And this actually perfectly illustrates exactly what's written in the core mathematics standards. To quote the standard directly, the radius of a circle is perpendicular to the tangent where the radius intersects the circle. This isn't just some random coincidence, guys. It's a guaranteed mathematical relationship that you can always rely on. Let's put that to the test with section 3, pause check on tangents. Okay, question time. If a radius is drawn to meet a tangent line right at the edge of a circle, what is the exact measure of the angle formed? I want you to literally pause the explainer right now, think about the theorem we just went over, and commit to an answer. Go ahead, pause it. Welcome back. So, did you get it? The answer is 90 degrees, or a right angle. Why? Because, as we just learned, the radius and the tangent are absolutely always perpendicular at their exact point of intersection. Great job applying that theorem. Let's move to see how this builds in section 4, inscribed angles and arcs. First, consider a central angle. Its vertex sits right at the exact center of the circle, and its sides are formed by 2 radii. But then, check out the inscribed angle. Its vertex sits all the way out on the outer edge of the circle, and its sides are formed by 2 chords stretching across the inside. Where that vertex sits, yeah, that changes everything. Now, both of these angles open up and basically catch a piece of the circle's edge. We call this the intercepted arc. Think of the intercepted arc as the crust of a pizza slice that the angle creates. It's the portion of the outer curve perfectly trapped between the 2 sides of your angle. So, here is the magic step-by-step reasoning for finding the relationship between an inscribed angle and its arc. Step 1. Identify your inscribed angle with its vertex resting right on the edge. Step 2. Follow its 2 chords outward to find that trapped intercepted arc. Step 3. Apply this golden rule. The inscribed angle is exactly half the measure of its intercepted arc. Let's quickly summarize these key facts about inscribed angles. They're formed by 2 chords, and their vertex is exactly on the circle's edge. And here is a really cool trick. An inscribed angle that rests on a diameter, meaning it intercepts a perfect semicircle, is always, without fail, a 90-degree right angle. How cool is that? All right, section 5, pause check on inscribed angles. Let's see if you've got this one down. An inscribed angle intercepts an arc that measures exactly 100 degrees. So, what is the measure of the inscribed angle? Once again, pause the explainer right here, calculate your answer based on that golden rule, and then hit play when you're ready. And we're back. Let's walk through the math together. Step 1, we identified the intercepted arc is 100 degrees. Step 2, we remembered our rule. The inscribed angle is always half the measure of the arc. So step 3, 100 divided by 2 gives us an inscribed angle of exactly 50 degrees. Brilliant work. Which brings us to our final stop, Section 6, Recap and Transfer Question. So the absolutely crucial points to remember today are captured in these 3 takeaways. First, chords connect points inside, secants cut all the way through, and tangents gracefully touch just once on the outside. Second, a radius and a tangent will always meet at a perfect 90-degree right angle. And third, an inscribed angle is always exactly half the measure of its intercepted arc. Which brings us to our final challenge for you. Imagine you want a delicious pizza slice created by an inscribed angle of exactly 45 degrees. Based on the rules we learned today, how many total degrees of that 360-degree outer crust will your slice intercept? Think about how to apply our rule in reverse. I'll leave you to ponder that tasty math problem. Thanks so much for learning with me today, and keep exploring the amazing world of geometry.